Marusic, also from University of Melbourne.
Okay, great. I'll just use the keyboard, that's fine, don't worry. It's okay, I'll just use that. That's okay. It's on. Okay, sorry about the delay. That's the title of the talk. This is a title with a slightly for a broader audience. It gives me a chance to acknowledge the co-workers. This is a considerable effort. It's work with Lex Smits, but also Dilip Chandran, who's joining us virtually today. Dilip led the experiments, did a brilliant job with help of Matt Fu, Ami Reza Rowley, and Daniel Chung is here. They did the simulations, and also acknowledge Dave Wine and Brian Hollingway, who are our industry partners for this project. And they brought the precision engineering, which really made this possible. So I'm talking about drag reduction using Spanwise wall oscillation. There are various ways to achieve drag reduction. This is the only one I'm going to focus on. So it involves moving the wall physically in a sinusoidal pattern with a traveling wave. This has been extensively studied in the literature for some time. There's a very nice review mentioned down there by Rico and colleagues that sort of gives the state of the art of the work in this area. And essentially it works. It works very well under the right parameters. At this Reynolds number of 1,000, we can see LES. So we're seeing those near wall streaks. And as you activate the wall, you move it, you see that those streaks are disrupted. And that manifests in, one, an attenuation of the turbulence level, but also the drag. And as I said, this has been extensively studied, predominantly through numerical simulations for good reason, because of the obviously needing to move the wall is quite complicated. But you can quite easily change those boundary conditions in a DES, a DNS or an LES. And on the right here, we've got the work of Quadrio, Gatti and Quadrio, and what's called the Quadrio map. So we can see that there actually are 4 parameters which you can change for the shear stress. And here he's mapped 2 of them, the circular frequency versus the wave number, the streamwise wave number. And you do that for a particular level of forcing. So A+ is the magnitude of that spanwise velocity, and of course Reynolds number. And you see that under this change from 200 to 1,000, things don't change too much. We can see here, can you see my mouse? You can, good. So you can see here the drag is optimal around here, or along that ridge. And when you go over here, you actually get a drag increase. Okay, so it's very sensitive to the parameters that you've got. As I said, this is a very challenging thing to do experimentally. I'll mention 2 very notable experiments, the work by Jonathan Morrison, where they use a Kagome lattice. So this is a very clever way of getting very large amplitude movements for small perturbations. And they were actually able to demonstrate this. You can see the setup is very complex, but they were able to achieve a modest drag reduction using this scheme. And there's been more direct approaches where moving them all physically with concentric rings here, essentially by Turi et al. And they were also able to demonstrate drag reduction. As I've mentioned, all of those studies are for one Reynolds number of less than 1,000. And so the big question, of course, is what happens as you go to higher Reynolds numbers? And that's where many applications are, and that's remained a question mark. That's what brought us into this problem. And I'll just refresh. I showed this slide in the first workshop about, let's go back and look at how does the boundary layer change, a regular boundary layer, as you change the Reynolds number. And the first thing we note at friction Reynolds number 1,000, it's very clear from this spectrogram, it's that near wall peak so in other words, this pre-multiplied spectra. If I take the integral over every line, I get the variance shown down here. I'm also showing the mean velocity for good measure. But you see, essentially, this dominates the landscape. However, as we increase the Reynolds number by about a factor of 7 or 8 there, or 7.3, you see that this very prominent outer peak emerges now and becomes very clear. You can see it exists even at lower Reynolds number, but it becomes very prominent. So this is these very large scale motions or superstructures, and everything in between is filled in with things that follow law of the wall scaling. Essentially, these are the attached eddies. So they make up this complex features that define a high Reynolds number boundary layer. I've marked here FP for footprint because we see that this signature, even near the wall, has this very large scale signal which extends down to the wall. And so this is something, and thank you, MK, for reviewing that. And essentially, this has been noted back all the way, going back to Narasima's work in the early 1970s. It's been disputed often because it's really seen as a heresy, because now we're challenging the concept of the law of the wall. But it's very clear that you do see these large-scale signals in the wall. I think in MK's plot at 5200, it's very clear. But even here at 2000, you can see that, so this is a simultaneous, and thank you, Javier, for making these available. It's cut off there. It's Hoyas and Jimenez 2006, friction Reynolds number of 2000. In fact, no, I don't know how to get rid of that, but that's okay. I don't know if I can on this screen. Anyway, it doesn't matter. Unless I can, no, I won't try. But essentially, if I, well, and I'm showing here, my Z is my wall normals. This is streamwise, spanwise. The top is a layer parallel to the wall in the log layer. The lower one is around that near wall peak, okay? And I can see those large elongated features, which your eye, at least my eye, is drawn to, and maybe I become biased when staring at them. But even at this, I mean, obviously there's a lot going on, then streaks are so small down here. We're talking about large features. So first of all, let's just focus on positive U, and you can look at negative, it's no different. And let's filter this. So we just filter this up till about 1 delta. And now you can see we're only looking at large features, and you can see a very clear correlation between the two. In fact, if I take that top, I change the color scheme, and I make that slightly opaque. I can bring that down on top of it, and you can see the correspondence is striking. You notice I've shifted everything to the left. That's to account for about 11, 12 degree angle of inclination that we know the structure has. And we see that in the skin friction as well. It's a little bit harder to see at lower Reynolds numbers, but if I was to filter these and cross-correlate them, you would have a significant value. In fact, if you go to high Reynolds numbers, so this is the atmospheric surface layer, you think you don't need to do any filtering. It's very clear. These are all in the log layer. This is at the wall. And you can see, again, that signal looks very much like that signal, at least for the low frequency components. And we can use, and I should mention, and that idea has been the basis of some theoretical work by Sergei Chernyshenko, and I'm sure we're going to hear about this in the next talk. So I look forward to that in terms of quasi-steady, quasi-hypothesis theory. So we can use those concepts to build up a model. And here, this is Philippe's work again. So essentially, I'm just showing a pre-multiplied spectrum of the wall shear stress. And I'm decomposing into 2 parts. Into the small scale, again, that near wall cycle, that's the blue. And then we consider a large scale component due to everything else, all those attached eddies, the very large scale motion, superstructures, and that's in red. And again, you can see that it's very small at this Reynolds number. We built a model which fits data extremely well up to here. And then you can extend that to any Reynolds number you like. The area under that curve is the variance. It's shown here. Again, it sort of agrees well, but you see that this gets larger and larger. So we do have the data. It's interesting, the data in the atmospheric surface layer, it was built, so the device is on the left there. What it is, it's basically a floating element, very light, and we measure its movement using the same principles in an atomic force microscope. So you shine a laser, you reflect on it. These are highly precise measurements. But you can actually, and so it's a very weak signal, but we believe we can measure it. And so if we actually looked at the spectrum, so the solid red line is from Utah for that, what we think is the Reynolds number. And you can see it captures that quite well. Obviously, we can't resolve those very small scales if they exist at all in the surface layer, but certainly for the larger scale seems to capture. So we have some confidence in those results. So the bottom line is I'm thinking about the boundary layer near the wall and the skin friction as having two components, large and small. So what does this have to do with drag reduction? Well, that's the next steps, because what we want to do is we want to, rather than all the previous work has really tackled that near wall cycle, we want to tackle the big structures and see, can we influence drag by tackling, and there's a very good reason why you want to do that, as I'll explain. And we're ideally set up for it in Melbourne. This is our large wind tunnel. What we do is we develop a boundary layer over a long length, so it becomes thick, and we get a naturally large Reynolds number where we don't have to drive the flow very hard. So for 20 meters per second or 30 meters per second, we can get up to 15 to 25,000. Actually, that's about 40 meters per second there, but we can do that. And importantly, and this is a crucial part of it, is having an independent measure of drag. And the best way to do it is to use a floating element. However, they're notoriously known for having a poor signal to noise ratio. Here we have the advantage of we can, because everything is so large, we can have a 3 meter long drag balance. So it's 3 square meters of surface which is floating on an air bearing. And that gives you a level of force that you can measure with a conventional load cell. And of course, the important thing is that the boundary layer essentially develops very slowly over those 3 meters. Essentially, it's linear. In fact, if I was to take the centroid and I use a Kalman-Schörner relation, I'm off by 2 millimeters in 3 meters. So it's a very good approximation. Also, this thing is built to handle very high loads. So it can easily handle anything we put in it without having the contamination that you get once you connect things. So we had to build a device, and the idea is that we will build something where we move the surface side to side. And you can see that here. You can see it running. This was the first generation. So this is, and all of this has to be done. This is slow speed. It goes up to 25 Hertz. So we go up to 1500 RPM. I always get nervous watching at those speeds. And indeed, this thing blew itself up. Essentially, that's running a 12, it's like running a 12-cylinder engine at 1500 RPM with no oil. That's essentially what we're doing. Any small hiccup, the whole thing just blows itself up. So we built a second generation, which we thought was a lot better. And we can do all of this with very high precision. And so it essentially mimics a smooth wall we're not running. So what we did is we have 4 of them. We synchronize it. We've put it into this drag balance. We take the fractional area and we can measure the force and we can estimate what the drag is. So this is when we first inserted it. I think that will start in a moment. So there it is in the wind tunnel. And we're going to turn it on in a moment. And you can see by running the motor either in one direction or the other, we can have the traveling way go upstream or downstream. And we can play around with that. Again, we try not to run this too much in the fear that it will blow up. So there it is now with the shrouds embedded. So give you a sense of dimension. So we're activating over 2.4 meters length, about 600 in width, and we can get some data. So here's some results. The top is where we've put a hot wire into the sublayer. In other words, it's a surrogate for the skin friction. And you can see that when you activate, that's the blue, indeed, you see that the mean value, this is normalized by the stationary shear stress, goes down. And that's about a 25% drag reduction. But you also see that the turbulence level drops. And that drop corresponds, so these are the results from the drag plate, and they correspond, that gives 25. So that's pretty good. That's within our uncertainty. So we have a lot of confidence in our hot wire measurements, but I don't think I'd ever believe this unless I had the drag balance to back it up. Okay, so let's look at some results. So here we have what we say literature. So this is essentially where current literature is. That's our LES, that's a DNS for reference. This is one chosen set of parameters. And what we see is that we can get up to 6. So here at 6,000 with this parameter set, we get about 27% drag reduction, which is pretty good. Because always a question, there's a lot of theories suggesting that it will drop off quite quickly with certain power laws. Here I'm showing the Gaddy and Quadrio prediction. This essentially assumes that the Quadrio map, if normalized by the local velocity, will not change. And so essentially what you're doing is you're assuming that any variation in the von Karman-Prandtl skin friction relation accounts for any variation in the baseline U tau, and that's essentially what you're seeing here. But it actually agrees quite well. I will note though, here what we're doing is we're activating at 140, which corresponds around 100, which is what the literature says is the optimal frequency to get drag reduction. And then what you're doing is you're activating around those small scales. So this is really in that sweet spot. And therefore, and it's interesting that it does get a result. Now, this is the bad news about this result, is that if you look at the net power savings, in other words, if I now subtract off the energy, the power I need to put in to drive that Stokes layer backwards and forwards, forget about the mechanical efficiency, just to move the Stokes layer is a cost, and it means there's no net power savings. That's why many people have quit working on this problem, because there are no net power savings, particularly now if you scale up to very high frequencies. So, but you know, what we're trying to do is activate large scales, much lower frequencies, and the power cost goes as omega to the 512. So it's very expensive. So now I'm going to call this large scale. So this is large eddy actuation at low. And you can see here, there's basically we get nothing, which is what the predictions were. But that's because more or less, there's nothing to really actuate here. The large scale signal is so weak that it really doesn't play any significant role. And of course, the GQ prediction, it's only going to drop from there. So what happens if you increase the Reynolds number? Sorry, first of all, yes, of course, the net power, well, this is just shows you that the Stokes layer cost is much less, but you've got no gain. So what if you got a high Reynolds number? So now what we do is, now we have more energy. So will something happen? That was really how we started all this. This was the big gamble we took. And sure enough, we saw a positive result. So now that's why we call this a different pathway. We've broken where what we're doing is activating at much larger scales. All the classic theory doesn't apply anymore. Now we see finite drag reduction and finite net power savings. Again, because the cost drops so much. Here, also, we're limited in how, I'd love to be able to run this at A+ at 12. I can't because the machine, I'd have to build a new machine because the stroke length has to be fixed. So I can't vary that, unfortunately, for this speed. But even here, we're getting around 10% drag reduction, which is pretty encouraging with the net power saving. So that's sort of the story. And 5 minutes, okay, so now a little bit, so I actually want to discuss, this is still, we're still thinking about this, but I wanted to discuss it because I'm really interested in talking to people. So if we look at, we can see the mean drops, okay? So on the top there, I'm showing the spectrogram. I'm marking where the location of the inner and outer peaks. I've called this small eddy and large eddy. Essentially what I'm doing, I'm saying that let's take something in between this white line. Anything below there, I'm going to call small eddy. Anything above there, I'm going to call large eddy. It's not, you know, but it's just a definition. But you get the idea. It's about the large and the small. But what we see is, depending on either, and again, here, this is less because A+ is less, I think. I think if you were to make that 12, I think this would be even lower than this. But that's an open question. Even so, we see that there's a broadband response. So there's an interscale communication going here. Even though I'm forcing at one frequency, I'm attenuating the turbulence across multiple scales. And importantly, in fact, for this case, I get, even though I'm activating at these large structures, I'm actually getting more percentage reduction in the small scales. So that's very interesting. And that sort of brings me to this really nice work by Beverly and her students Davuri and Jacobi, looking at triadic interactions. And these are my take-home messages. One is that triadic interactions naturally arise from the quadratic nonlinearity of Navier-Stokes. And in fact, that's what we saw George and yesterday, Jovan talking about that, okay, Jovanovic, showing the Mihailo's talk, indicating those sort of results. Interesting, what Beverly's group did is they took a boundary layer and they put a simple harmonic forcing on it by perturbing some roughness. So it's purely harmonic. And what they find is that once you do that, it's a slow frequency. What happens is that the smaller scales in the boundary layer near the wall tend to phase lock with that low frequency. Okay, so that's that triadic interaction. And this is obscure, but there's a reason why. Skewness is actually an average measure of the phase in these triadic interactions between scales. I'll just explain that really quickly. If I just take a Fourier series of the fluctuating velocity and I just say, okay, at a given cutoff frequency, everything below there is large, everything above there is small. I can decompose the velocity into large and small. I expand the skewness and I see these terms, okay? So if I do that, this term stands out, and Davuri and McKeon show this explicitly. This is exactly this, and that is the triadic interaction that occur across this filter cutoff. And this quantity, sine of this difference, is a measure of the phase difference between the large scale mode and the envelope of the small scales. Okay, so we'll keep that in mind. So what has this got to do with drag reduction? Well, we look at those terms in skewness as a surrogate for scale, and we see only, so what happens is, so sorry, I should mention, this is drag reduction, this is not linear. I'm just simply comparing numbers, okay? This is not a linear axis. So, but what we see is as the drag reduction goes up for both small and large eddy actuation, is that the skewness goes up. And that skewness increase comes from two terms. One is the small scales, and these are the triadic interactions of just the small scales, which is essentially a reflection of increased dissipation, which we expect. Drag reduction went up, we expect dissipation to go up. But we also see that this phase relationship, this term, also goes up. So what we're seeing is that things are getting more in phase. So the conclusion here that our takeaway is that increased drag reduction is associated with a stronger coupling between, and that explains that very broadband response that we get. In fact, if we do it explicitly here, what we do is we calculate the phase of the co-spectrum formed between the large and the envelope and the small, and I see it goes down, it gets closer to zero. So this shows directly that they get becoming more in phase. And I'm about to wrap up. One last point, but a very important one. If you look at the trend of skewness near the wall, you see it goes up. And that all comes from this term. This is the sum of those other terms. This term changes with Reynolds number near the wall. So a boundary layer naturally, as you increase the Reynolds number, the phase relationship between the large and the small, as you saw, the large scales get more and more energetic and become more prominent. They start bullying their way around, and essentially the small scales follow in suit. So drag reduction, this strategy should be even better at high Reynolds numbers, because naturally the flow is aligning to that. So there's my conclusion, and it's done with a cartoon. So there's two ways to get drag reduction here. You can either target the near wall. It works tremendously well, but it comes at a huge cost, and you're in the red. And what happens when you do that, the large scales become phase locked or become more in phase with these small scales. Alternatively, if you activate at the largest scales, that also leads to this phase coupling or things becoming closer in phase, but this costs much less. And then we have green, okay? Green is good. And importantly, this is my conjecture, that coupling and interaction between the large and the small increases with increasing Reynolds number. So I think you can, quite often when we go to high Reynolds numbers, just doom and gloom. In fact, here, there's a better story. I think it'll work better as you go to high Reynolds number. And I'm not proposing we now start moving walls on planes, but the idea is that this shows us that there are ways by activating those scales in whichever way someone may devise can be very beneficial. So thank you. I'll stop there.
Thank you, Ivan. Rich and Ali.
Thanks, Ivan. Really interesting stuff. My question, when you see a turbulence reduction in the turbulence levels, do you know if this is kind of a damping of the production or a shortening of the turnover time, you know, faster cascade? Do you know what's the mechanism?
Yeah, it's a really good question. There's a lot of literature on this. I mean, I'm still thinking about it, but clearly moving the wall does disrupt the streaks in a particular way. They break down as a result. As MK showed, there's a lot of energy transfer in that inverse direction. So if you kill the small, you're basically starving the others and they become more. And so, yes, you're actually dampening the turbulence. You're killing off. So yes, dissipation goes up normally, but in terms of the exact mechanism, it's still quite open. I mean, for me, I don't fully understand it.
What is the value to the amplitude of the wall oscillation, spanwise wall oscillation, by respect to the typical wavelength in the spanwise?
Yeah, so we chose, so this is really, we had to make an estimate. So I made an estimate based on around the wavelength is about 1 boundary layer thickness in terms of the wavelength. How important it is, I don't know, but more important, that spanwise velocity around 12 seems to be the magic number. That's about the convective speed of the big structures as they in the skin friction as they move along the wall. So you need to target things around that convective velocity at the wall, and it makes sense. You could get away with less. Remember, we're moving the wall. Stokes layers are they're horribly inefficient at transferring momentum. You know, so if you could build a body force that target things around those streaks at 15, you get a much more bang for your buck.
So even this was absolutely fascinating. As you mentioned, at lower Reynolds numbers, there are lots of studies that indicate that T plus of 100 gives you the optimal period of oscillation. So as you move to higher Reynolds numbers, obviously that's uncharted territory in terms of theoretical developments and simulations. Are there efforts that are moving in that direction to try to identify optimal period of oscillations?
You know, this is where I think theory can help us tremendously, because doing this by experiment is, you can see how much complexity, and essentially if I want to start changing parameters, I have to start building new rigs. I'm not going to do that. I'll be well retired. But the same reason, why has no one seen this before? Simply because you have to go to high Reynolds number. You have to, because these large structures are going to be important at 1,000. You know, the 2,000 there, but they're still not active enough. So really, but once you start getting at 10,000, 100,000, they're the main show in town then. Okay, that near wall cycle is always going to be important, and 100 is always going to be good, but it's just the expense. But this is a really good question. And unfortunately, I don't think we can do it just by brute force, by doing lots of simulations. Maybe LES can help, but still here we've done wall resolved. You know, would I trust a wall modeled LES? I don't know, maybe. Yeah.
Another good topic for discussion. So let's thank Ivan again. Okay, and our final